Thanks. Well, thanks a lot for the organizers for giving me the opportunity to speak and for having such a great conference so far. I've really enjoyed all of the scientific and non-scientific activities. Yeah, so I weakened the title a little bit because categorical W types are the motivating example of this work, but I'm not really going to talk about them. I'm going to talk about the theory of which they're an example, so I didn't want to focus so much on that in the title. Okay, so here's the theorem, just to put the theorem up on the board, like Joachim did, and then I will try to explain the theorem in the rest of the talk. So we're thinking about endofunctors, in particular polynomial endofunctors, our favorite example, and we're motivated by what people are interested in the denotational categorical semantics of functional programming languages and type theories and stuff, where they're interested in initial algebras of endofunctors and terminal coalgebras of the same endofunctors. And so in our paper, we prove that if we look at the category of algebras, not just any endofunctor, but a lax symmetric monoidal endofunctor, also accessible, on a locally presentable symmetric monoidal closed category. That category of algebras is enriched over the category of coalgebras of the same endofunctor. And that's what appears in the two papers that are already out. And then in my master student, Lucas Mulder thesis, he made this a bifunctorial in F. Okay, and so there are many examples, even though these hypotheses seem quite strong, in particular including polynomial endofunctors whose initial algebras are called categorical W types. We'll talk a little bit more about that. And so we see that this category of algebras, which is historically of great importance in the semantics of functional programming languages, has more structure than people realized before. And so also in our paper, we try to exploit this structure and kind of give a proof of concept, let's say, of how you could use this to do something. And so we generalize the notion of W types by generalizing the notion of initial algebras, not exactly as an instance of a weighted limit or colimit, but very similar to that. Okay, so before I talk about our work, I want to talk about previous work that has the same phenomenon. So there was this original work by, Sweetler, the algebraist, and Raith, let's say, the category theorist. So Sweetler had this phenomenon in his original book about algebra, and Raith immediately realized that it was a categorical phenomenon about enrichment. So there, Sweetler is talking about a field K and K algebras in the traditional sense. And he talked about universal measuring coalgebra between A and B, and then Raith immediately recognized that was an enrichment of categories. And then, of course, I mean, it's kind of associated by the fact that I'm saying that this universal measuring coalgebra that Sweetler constructed underlies an enrichment of the category of K coalgebras and the category of K algebras that we can extract from these enriched terms the original unenriched terms. And indeed, there he gives a nice characterization of what are called the group-like elements, or I will use the term set-like elements that represent the actual algebra homomorphisms between A and B. Okay, and then following that work, there were many other pieces of work. So Rendall and Joyal showed that DG algebras are enriched in DG coalgebras. Here monoids are enriched in comonoids. V categories enriched in V co-categories. Infinity algebras are enriched in infinity coalgebras or infinity algebras. Monads enriched in comonads. And here we're talking about algebras of endofunctors enriched in coalgebras. And at the end, I'll talk a little bit about work in progress to see more instances of this. Yeah, so maybe one point of this talk is just to advertise this phenomenon that's happening everywhere. Maybe, you'll see it in your favorite category of algebras. Okay, so to talk a little bit about the motivation, in particular about W types, as I said, this is important in the categorical semantics of functional programming. So there, when you're programming, you're using various types which correspond to objects in a category, and most of the types that you're using there, well, sometimes they're function types, but if they're not function types, then they're being defined inductively. And so I'm not going to bring up any syntax because luckily we're all category theorists, so I'll just explain it in terms of category theory. When we define these inductive data types in functional programming, what we're doing is specifying a polynomial endofunctor. And then in the functional programming language, we regard that specification as just immediately picking out the initial algebra, which categorically is usually called a W type, or also in type theory it's called a W type. So categorically what we're interested in for the models of these things are initial algebras of polynomial endofunctors. So here I have two basic examples that hopefully you can believe, if you're not into functional programming, are useful for programmers. And they're both polynomial endofunctors, though I'm not really writing them explicitly like that. So of course, as category theorists, we know that the natural numbers in a topos is the initial algebra of this endofunctor. So in this talk, I'll focus on just the situation where we're in set. So here, this is the copy, this is the terminal object in set. And the terminal coalgebra is maybe a little bit less famous, but we write it like this. So it's the natural numbers plus a point at infinity. And this functor is going to constitute our main example, both in paper and in this talk, because it very easily satisfies the hypotheses of our theorem and kind of illustrates what's going on. Here's a slightly more complicated W type, generalizes the natural numbers one. So if we want to get the type of list in a functional programming language, we want to write exactly like this, but basically we specify this endofunctor, and the type that it produces is the type of list in a given set, type A. And the terminal coalgebra generalizes this guy, and we call that the set of streams in A. So this is the set of lists, but also infinite lists. So these lists are finite, and the streams include also infinite lists. And this functor also satisfies the hypotheses of our theorem, but we need a little bit of extra algebraic structure, because if you remember, one of the hypotheses was that this functor is lax-monoidal. And if you kind of unroll what that means that we need a little bit of extra algebraic structure on this. In particular, we need the structure of a commutative monoid on our original guy, A. Otherwise, that is in another example. And we'll see more examples at the very end. But those are motivating examples. Okay, so does anybody have any questions about the introduction while I take a drink? Okay, so now for the content. So here's a definition of measuring. So I said that we have an enriched category where the enriched columns are defined as these universal measuring coalgebras. So now I'm going to define that. So here are our hypotheses again. And we've got two algebras that we're trying to take an enriched column between. And that enriched column is going to be a coalgebra. So we define a measure between these algebras to be a coalgebra, together with a morphism. And here, so we're assuming that C is closed. So here I'm thinking the internal hum of C. So I'm thinking about a morphism of like the underlying object of our coalgebra into this hum, satisfying this diagram. There are maybe better ways to motivate why this diagram, which looks a little bit complicated, is appearing. But in the interest of time, I'll just say that we have these morphisms, alpha, beta, chi, and phi, and this is kind of the way to put them together and ask that they cohere. So this is a measure, and we say that the universal measuring coalgebra is the terminal one, and this is going to be the enriched hum. Okay, and then here's our theorem again, and Mulder, my student, extended this to make it functorial in F. Okay, so the rest of the talk is going to try to explain what this looks like, in particular in the example of the natural numbers. Right, because we have now this big hammer coming from category theory. We have this very obscurely defined enriched category, and what is it? What is the extra information that this enriched category is actually carrying? That's the question I think now. Okay, so everything regarding the natural numbers will be in red, so you can tell when I'm talking about this example. So if we just spend 5 minutes, which we don't have, to kind of unravel the diagram on the previous slide indicates that we're in the category of sets, and we're looking at this endofunctor that takes x to x plus 1. Then we can write down kind of point-wise what the diagram is saying measuring is. So there I'm measuring is a coalgebra together with a function from this underlying set C into the set of functions from A to B, such that, so I'm writing now, I'm going to call this f here, so meaning that the function here is f, and then C I'm going to write it as a subscript, and I am writing it here. Okay, so for any C it takes the base point to the base point. So an algebra for this endofunctor has a base point and it has an endo function on it, which I'm writing plus 1. So it takes the base point to the base point for any C. It takes a successor to the base point if this is 0. And so by this symbol I mean that, okay, so C is a coalgebra, so it automatically gets a universal morphism to the terminal coalgebra at infinity. And so we can call that universal morphism by these brackets and say it's kind of an index. And C is measuring actually how many times you have to apply the partial endo function that is the coalgebra structure to get to the undefined element. So if you only have to apply it, well, once, which here is 0, then we want to say that any successor there for that kind of C is taken to 0. And here we see something that looks very much like the second criterion you would expect for algebra homomorphism, but kind of, let's say, twisted by this this action -1, which is how I'm writing the partial endo function that is the coalgebra structure on C. Okay, so that's what the definition of measure unravels to in this case. And again, the universal measure is a terminal one. Okay, so still I think the question is, what is this? Still a complicated specification. So let's start to look at it in specific cases and see what it's telling us. Okay, so just by virtue of me saying that this underlies an enrichment of algebras and coalgebras, by that I mean, I'm taking that to include the fact that if we take the points of our Hom coalgebras, or enriched Hom, then we get back to the ordinary category. So indeed, we get back to the ordinary category. The Homs there are just algebra homomorphisms. But we can ask, actually, how does this work out in our particular example? So in our particular example of natural numbers, again, the set-like elements are this, which we know by categorical nonsense is just going to be, the points like this are just going to be alg-AB, non-underlined, by which I mean the algebra homomorphisms, the set of algebra homomorphisms. So our unit here, our modal unit, is built on top of the modal unit of set, so its underlying set is just a singleton. And its coalgebra structure just takes it to itself over and over again. So a point like this is a special element here in the underlying set of this coalgebra that's taken to itself over and over again by the coalgebra structure, which is just a partial endomorphism. And so if we think about what this means, if we look at the definition of measuring the relevant parts, then we're asking, we ask here for this and this. But if C minus 1 is C, I mean, we just have a star, and star minus 1 is star, then we see these two requirements, which are just the definition of an algebra homomorphism between algebras for this endofunctor. So we see that this requirement just means that our star here, which I call star here and F star here, is a total algebra homomorphism, which is an element of this set between A and B. So indeed we find that these set-like elements are what we think they are. And here, I would just now pull, I mean, if this type calculation explicitly, but I would just pull this one out of the hat. So we of course know that N is the initial algebra of this endofunctor. So the set of algebra homomorphisms from it to any other algebra, of course, is a singleton. But we can calculate that the enriched Hom, this coalgebra from N to A, is an infinity. Okay? And so the point here, so we should, if we took the points of this guy, we should see it extracting exactly this point. And indeed, it's extracting exactly the point at infinity. So the only point in this sense of this Hom coalgebra is just the point at infinity. But what are now the non-set-like elements? So the set-like elements are the things that already existed in our original category. They're the elements of the Hom sets. But what else is happening in this Hom coalgebra? What is the extra information that this category has in it? So I said that we can calculate this, and so then we could denote the elements of this Hom, of the underlying set of this Hom coalgebra like this. And maybe I'll go a little bit quickly through this in the interest of time. If we look at the definition of measuring, we see that the first one has to take everything to 0. The second one has to take 0 to 0, and then everything else to 1. And similarly for the second one, it takes the first thing to take 0 to 0, 1 to 1, and everything else to 2, etc., etc. And F infinity is the identity. Or not the identity, but is taking n to NA, by which I mean the nth successor of the base point of A. Okay, so we call in our paper the elements of the underlying set of this Hom coalgebra and partial algebra homomorphisms, because they're kind of doing the right thing up to step n. So it's like you want to construct a total algebra homomorphism from n to A, step by step. And so here you just focus on where 0 should go, here you focus on where 0 and 1 should go, then you focus on where 0, 1, and 2 should go, so you're building up the total algebra homomorphism inductively. Okay, so let's look at another example in this case. So we're focusing in the last slide on capital N and arbitrary algebra A. So let's just consider a slightly more complicated algebra. So we could think about the quotient of N by this relation. So it's really just the algebra that has elements from 0, 1, dot, dot, dot to N. And we have a kind of dual thing of a subobject, a subcoalgebra of N infinity, which has also in this underlying set elements from 0 to N. And we can ask what are the Hom coalgebras here in this slightly more complicated case. So if we think about it for a second, we know that in the category of algebras, we're asking whether or not there's a morphism from N to A. There is one exactly if A has this same quotienting relation, but otherwise there isn't going to be one. So we're basically asking if the unique morphism from capital N to A factors through little n. And then we can calculate what this Hom coalgebra is. And we see that in the first case, it's N infinity, just like before. But in the second case, where this is just nothing, here we find this Hom coalgebra that has an underlying set from 0 to N. So this calculation is now telling us more information than we had before. It's telling us where in this kind of induction that I described in the last slide, we fail. Okay, so we can send 0 to the 0 of A, we can send 1 to the 1 of A, etc., etc. And at some point, if A doesn't have this relation, then we can't continue. And that's what's being recorded here. And just like I said before, if we take the points, we should end up here, and indeed there are no points here because there's no element here in section itself. Okay, so we try to, in the paper, explain what you could actually do with this extra information. So we generalize the notion of initial algebra in the following way. So we ask that there's, for a C initial algebra, for coalgebra C, that there's a unique coalgebra morphism like this. And then we prove that N is the N infinity initial algebra, which we interpret as kind of meaning that it's initial with respect to total algebra homomorphisms. And just like in the last slide, we kind of did some calculation involving this guy, and we got this guy. Now we have kind of a backwards operation where we find that little n is the n-circle initial algebra. So we think of that as meaning that it's initial with respect to partial algebra homomorphisms. Okay. And again, I won't get too much into this, but for the semantics of functional programming, it's these initial algebras that are interesting, so it's maybe interesting to generalize them. Okay, we have many examples. So, the identity is an example. The constant functor at a fixed commutative monoid is an example. It's closed under composition and tensoring and coproducts with some extra hypotheses. And we also have W types, like I said, but we do need some extra algebraic structure to get our functor to be Laxmanoidal. and also, interestingly, the discrete equational systems of Leinster. Okay, in the last 2 or 3 minutes, I will, I guess I have a little bit more time because I started a little late, but I was still trying to be in time. Okay, so the last part, I will talk about work in progress. So it's a little bit hard to talk about old work. I always just want to talk about what I'm thinking about at the moment, so if you'll indulge me, I will do that a little bit. Okay, so here's a proof sketch of the main theorem. So I didn't really give any intuition about the main theorem, just what it means. So very roughly, we prove the main theorem. Actually, in the paper we prove it in several different ways. But if you think about what is the thing that makes this theorem go through, what's happening is that we, by hand, can construct a functor like this that we call the convolution algebra, I think based on previous work like the work of Sweezler. And then we do some adjoint functor theorem stuff to switch things around and get a functor like this. Okay, so let me explain a little bit about what this functor is doing. So on objects, we take a coalgebra C and an algebra A, and we put an algebra structure on the internal HOM in the underlying category from C to A. And this algebra structure is this composite. So the first arrow here is the lax monoidal structure appearing, so I didn't label it. And the second arrow here is precomposition by chi and postcomposition by alpha. And like I said, then we just use the adjoint functor theorem to turn things around into a functor like this that then underlies the enrichment. So we can think about like in what other situations this strategy works. So could be interesting to vary F and G. So there's a concept called FG dialgebras, which is a category of pairs like this. So the algebras that we've been talking about are F-id, like F identity dialgebras, and the coalgebras are identity F dialgebras, so a generalization where we generalize the identity functor. So we can think, can we make this theorem go through in that case? And indeed we can. So we can produce a convolution algebra by putting an algebra structure on this internal HOM CCA in this way. So here we use the lax monoidal structure of F and the co-lax monoidal structure of G. And here again we pre and post compose by the coalgebra and algebra structures. Okay, so dialgebras, it generalizes algebras and coalgebras, but it's a little bit niche. So then you think, okay, why are these x's the same? Of course, as category theorists, we're extremely interested in common categories. So the x's could be different. It could be x and y. And so we do exactly the same thing. And indeed, we find that, under these strong hypotheses, that f down arrow g is enriched in g down arrow f. And indeed, if you really think any kind of diagram that can be partitioned into two parts that we could switch would satisfy this under maybe some strong hypotheses. So in particular, you can think like cones, so you can encode like cones and cocones as common categories. Cones are enriched in cocones and cocones are enriched in cones, but with these strong hypotheses. So that's future work to figure out when could that be interesting with these very strong hypotheses. Okay, so in summary, we have that algebras are enriched in coalgebras under rather strong hypotheses, but in our main paper we show that functors of interest satisfy these hypotheses. We try to kind of extract the meaning of what this enriched category is telling us, which we interpret as being about partial algebra homomorphisms, examples as I said, and then we kind of try to use this to generalize the notion of initial algebra, maybe heading towards applications in functional programming, and of course we want to generalize this and understand exactly when we see this phenomenon occurring in category theory, because from all the papers that I listed, we see that it does occur quite a bit. Okay, that's it.
Thank you very much. And we have a few minutes for questions. Yeah.
I looked at your diagrams before the talk, I couldn't. Does your measure diagram reduce to the well-known case of coalgebra to algebra homomorphisms? I couldn't see how to substitute a trivial case for the domain of the algebra map. So you've got going up by chi, along by f phi, and down by beta, the same as going across by phi. I couldn't see how to substitute a trivial a to do that, but it seems to be ought to be the case.
Yeah, I also don't see right now how to do that. But yeah, I mean, you're right that it does bear some similarity, so maybe it's interesting to think about. Yeah, thanks.
Maybe I missed it, but do you assume that F is laxinoidal? Oh yes.
Yeah.
There you go.
I do.
Okay, and that gives you the monoidal structure on the coalgebras.
Yeah, exactly.
Okay.
Yeah.
Here you note the notion of algebra and coalgebra over a Mendel functor.
Yeah.
Are there some of your results you carry over when you look at algebras and coalgebras over monads?
Yeah. So that's also the next kind of interesting question. So, I mean, here we're asking that the underlying the functor that we're taking the algebras and the coalgebras for are the same. I guess in the end I had two functors, but it was the same for the algebras and the coalgebras. We're just kind of switching things. In the paper, in the second paper that I listed, we do generalize this to okay, I'm going to probably get it backwards, but the F algebras being enriched in G algebras, where I think G is a kind of module over F. I might have that backwards. And so maybe that kind of points in the direction of having different functors, and in particular having like algebras for one monad and coalgebras for one comonad that interact. And I think also Richard has thought about this a little bit. Yeah.
Any other questions? Or in that case, I think let's. One more question.
No, doesn't matter. Maybe.
Thank you very much again.